And the next speaker in this session will be Avery Ching, who is at Facebook and will be telling us about how to do graph processing at Facebook scale.
Thanks. We want to thank the GraphLab folks for giving us an opportunity to talk about the problems that we face at our company. And in the interest of time, I'll just jump right in. So the motivation for why graphs are important at Facebook should be fairly obvious to most of you. Hopefully some of you use Facebook. We have a friendship graph, which has over 1.1 billion monthly active users, more than a couple hundred billion connections. And we also have other graph projects in Facebook, such as the Open Graph efforts, where application developers can connect their objects with real-world actions, such as Avery's watching The Walking Dead, or Avery is presenting at the GraphLab conference, things like that. So we've got a lot of data to process. We have huge graphs. And our motivation can be basically summarized into 3 different areas. So the first area is in ranking. We have products such as newsfeed and search, where we've got a lot of different kind of content to show you, whether it's posts from your friends or pictures that I've recently, from that crazy night you had at the bar yesterday. And we need to find a way to provide really good quality ranking features and signals to make sure we provide relevant content for users and something that provides ultimately for a really good user experience. The second area we focus on is in the area of recommendations. We have products such as people you may know, pages you may like, and we can also recommend groups for you to join and events for you to go to. This area of recommendations can be done in a variety of different ways, and this is something that we're focusing on for providing better user engagement. The third area of our motivation is in the area of clustering / graph partitioning. These are really old problems in computer science, and but they have practical foundations for why they're useful at Facebook. So for example, if you can imagine a very simple implementation of how newsfeed would be done. You would have users and their content stored across a variety of machines. When someone clicks on the newsfeed, I fetch that content from a variety of different machines, and then I rank those objects and then show them to the user. Now, if we can actually do things like clustering users together in the same sets of machines, we can reduce network traffic, we can reduce CPU usage, and ultimately provide lower latency and a better experience for our users. All right, so the project that we're using at Facebook is called Apache Giraffe. There's been a lot of speculation about what we're doing with regard to graph processing, and I can tell you that our team is pretty much the only team doing large-scale graph processing at Facebook. And we're doing this at the scale of, again, hundreds of billions of edges or more. And the technology itself is inspired by Google's Prego project, which was inspirational to a lot of graph projects. The major difference between it is that it runs in Hadoop and is open source. And this is really important to note because by running on top of Hadoop, we get to leverage all the existing infrastructure that many companies already have in production today. And we can just leverage a lot of operational experience in terms of running Hadoop as well. So the model is, in some sense, similar to GraphLab. You think like a vertex. Imagine you're a vertex in the graph. You can do some arbitrary computation on it, for instance, changing your vertex value, your page rank value. You can send messages to other vertices in the graph. And it has a very simple, and this whole thing is actually from something called bulk synchronous parallel, which is from Leslie Valiant. So I'm just going to run through a quick example because, as some people have mentioned, this conference has grown a lot, and some people may be new to what Prego is. So I have a very simple example here where we have a strongly connected graph of 3 nodes. Each one has a different vertex value, and we want to basically figure out, for all the vertices, what's the highest value of the vertices across all of them. So I can do this in 3 steps, in 2 simple steps. First, if you have first of all, you propagate your vertex value to your neighbors. If you haven't received a higher vertex value, you're done. You're done. Otherwise, you then propagate your new higher vertex value to your neighbors. So after the first iteration, the middle vertex has received a higher vertex value of 5, and it propagates it to its neighbors. And the lower vertex then receives that value of 5. And now everyone finally agrees that 5 is the highest vertex value. So this Prego / graph model makes it really easy to do these graph computations by thinking like a vertex. Giraffe works on top of the existing Hadoop stack. And for Facebook, this is something really important. All of our data is stored in Hive and / Hadoop. And actually, most of it, 95% of it is actually stored in Hive tables. So for us to be able to access our data, whether it's Hive or HDFS even directly, is something really important for integration at the company. And Giraffe makes this simple because it runs as a MapReduce job on top of our existing infrastructure, and again, leverages the same operational expertise we have from our engineers. We support a whole bunch of different versions of Hadoop, including the Facebook one, which is actually customized. This makes it really easy for us to even try out different versions of Hadoop if we wanted to. But also for those of you in the audience who have companies that are trying different versions of Hadoop, you can actually try out Giraffe very simply on your existing infrastructure. Here's the data flow. First of all, we load the graph. We have a way of specifying data sources and then converting them to edges and/or vertices. You can actually have an arbitrary number of data sources, which allows us to do things like construct graphs on the fly. And at Facebook, while partitioning is a really interesting thing to look at, we have tons of graphs to process every single day. And partitioning each of them just for one run of a computation is not really practical. So what we do instead is we load these graphs up, we generate them on the fly, we create the edges, the vertices that are associated with them, and then we run the algorithms. So you specify a bunch of data sources for your vertices and edges. You load them up into memory across a bunch of workers, distributed and parallelized. And then you execute the computational part of your workload by changing your vertex value and/or sending messages to other vertices in the graph. When we're done, we just dump everything back into Hive as tables. And then at that point, what we can do is just simply have our Hive instance for later analysis. Or you can actually use another interactive system that we have custom built at Facebook. But we've actually taken this Prego model and moved a little bit beyond it to support the needs of our applications. Actually, to be honest, everything we do at Facebook is grounded in the applications that we have and the user requirements. We're not trying to build necessarily the fastest graph processing system for every single use case out there, but rather to serve the needs of our existing applications. And one thing we've done is create this idea of sharded aggregators. So aggregators in the Prego model are a kind of shared state among all vertices in which operations that are associative and commutative can then be propagated, can be aggregated together and then propagated to everybody, all the workers that are participating in an application. One thing we've done is sharded them for better performance, and I'll explain in a use case later. The next thing is we've added this idea of master computation. Master computation is actually something from the Stanford GPS system that they contributed to us, but it's really important because it allows you to do some small serial computation before you actually execute the computation of your graph for every single iteration. This allows you to actually compose, to actually have some control logic about where your application is going as it's proceeding. And the third thing we added is something called composable computation. So we've actually taken this idea that the vertex is integrated with the computation, decoupled it, and allow you to actually build reusable components of computation and integrate them with your different applications. The easiest way, of course, is to just look at this through a use case. So let's take something really simple and straightforward, just a really easy example, which is k-means clustering. The idea behind k-means clustering is to take some input vectors and cluster them into k-clusters where there are centroids that are basically the mean of the clusters. So let's begin with some random centroid locations, and then we basically find the closest centroid to every single input vector and assign them to that centroid. Finally, once we have the new assignments of the input vectors to their centroids, we then update the location of the centroid based on the mean of its input vectors. And then you can rinse and repeat over and over and over again until you hit convergence. So specifying this in Giraffe is actually quite straightforward. It's very easy to partition the problem. You just think about input vectors as being vertices, and they're naturally partitioned across machines, which is part of the infrastructure itself. The next thing is the centroids. Centroids can be modeled as aggregators, and aggregators are just, again, shared data across machines, so they're, as you can see the example, all workers have all aggregators. So this is great, right? We're done. We can just go happily cluster everything out there, and we're happy. Well, there's a problem, though. So sometimes you have massive dimensions. For instance, what if I wanted to cluster all the Facebook users by their friendships? That means I would have 1 billion dimensions. And k-clusters, which means every worker is sending their master a really large amount of data. And what ends up happening is that either you run out of memory or you hit a saturated network link. So to solve this, we implemented sharded aggregators. So the original Prego design is that you have this master and a bunch of workers, where the workers actually send data to the master, where they're aggregated, and then broadcast back to all the workers. And having a single point of contention there basically slows everything down. What we can do instead, since every aggregator actually represents a centroid, is distribute those centroids across a number of workers and then split up that workload and get better performance, as well as better scalability. We haven't looked at a tree-based optimization, but they're kind of orthogonal. You could do both here in this case. We haven't really seen this as a problem. Okay, so great. We've got this k-means application that can work on high dimensions. And now, since we're actually clustering by friendships, it might make sense to actually check the metric of how well are we doing our clustering in terms of cutting the number of edges. Here I have a small illustration where the dotted lines actually represent cut edges in the graph. So we're trying to minimize that. So 2 phases. First thing is you just send all your out edges, your cluster ID, and then in the next phase, you're going to aggregate those edges with your different cluster IDs, and you can easily compute the edge cut metric this way. Very simple. But now I don't want to do this too often. I want to only do this really like once an hour at most when I'm clustering. So how to express this inside a computational framework like Giraffe? That's where we added master computation. So master computation basically allows the master to do a little bit of work just before the superset starts. This allows it to direct the way that the superset works. So in this example I have, we're doing k-means. The master tells the workers to do k-means, then k-means again. Then it realizes it's time to do an edge cut. At that point, it directs the workers to do the actual edge cut, and then it finishes that edge cut, and then goes back to k-means. So this was actually contributed by Stanford, and we're happy to have it because it's a very useful feature in our production applications. Okay. Another problem you might run into. All right, so now let's go back to this idea of how do you initialize the centroids. One thing you can do, since this is a friendship graph after all, is to start with a bunch of random input vectors that we add to centroids. And then we want to tell a few random friends of those input vectors to also add themselves to the same centroid. So this is pretty easy. You do some random sampling. We send some messages to our few random neighbors. And the next stage, they're going to add themselves to the centroid. We're all happy, right? Except for, again, this is really hard to express now. Because we only have a single message type, right? So if I want to actually send different types of messages, I have to hack up my message, which makes it really nasty. Similarly with combiners, I only have one combiner that I can use for my entire application. So this is troublesome as well. Plus, my code's really getting messy, and I don't like messy code personally. So the idea is that we would actually decouple the vertex from the computation itself. So putting together our entire example that we have, first thing we would do is have a computational phase to add those random input vectors, as well as select those random friends to also add themselves to the same input vectors. And what we do here is we have split up messaging. So we use an in message type and an out message type. So in this first phase, we're just going to send the centroid message, which contains the centroid ID, so you should add yourself to this centroid. And there's no combiner for this case. And then in the next phase, we can actually add ourselves to the centroid if we've been selected by our friends. Then we start doing k-means. Then we have a way to do our edge cut as well, because we can specify these in and out message types. And master is responsible for setting this computation and the combiner classes. This makes the whole process like really reusable and composable. So we can take the same edge cut phase of our code and actually put it into all our different partitioning applications, all our clustering applications, without having to rewrite it from scratch. And similarly, we can do this with any stage that we actually have. Additionally, we can also take advantage of better combiners we have for individual stages. Okay. So let's compare this to Hive. I mean, Hive is for some of you who don't know, Hive is actually a SQL implementation essentially on top of MapReduce. And Facebook developed Hive a long time ago. We have some tweaks that make it quite a bit faster than the actual open source Hive. And for PageRank with 400 billion edges, we did a comparison between something that was running in Hive or kind of running in Hive. It would take more than a day to do basically. And we could do it in Giraffe 120 times faster in terms of elapsed time. So we were able to enable an application that wasn't possible previous to this. And in terms of CPU resource, in terms of CPU time, we actually were able to reduce this by 26x. And just to look at a different kind of application, we have a friends of friends score. So friends of friends score is basically a calculation where you calculate the strength of a friendship between two users, A and B, based on the strength of their mutual friends. And this is actually not really an iterative algorithm, but it still performs much better in Giraffe than compared to Hive. So with 71 billion edges, we can see a speed up of almost 50x. So for scalability, we ran some quick experiments. What we have here is a PageRank benchmark with, in this case, random edges. We have 200 billion edges on the left side, and we are changing the number of workers. And so if from between 50 to 300 workers, we see that Giraffe exhibits pretty much linear scaling properties, which is pretty good for our use case. And on the right side of the graph, we fix the workers to 50, and then we scale up the edges from 1 billion to 200 billion edges. And we see that as we expect, the problem size should also scale with the runtime. But let's be honest. The billion edges is not that cool, right? It's kind of boring. So we decided to look at a little bit, bigger use cases that we had at Facebook. And what we wanted to do in this case is actually construct a real graph made out of, users and real edges between them. So we have friendships, we have subscriptions, we have public communication, we have a bunch of other stuff that I can't really talk about in detail as a way to construct this huge 1 trillion edge graph that's made up of real social data. And we said, what happens if we throw Giraffe at it? We're going to run PageRank. No partitioning. So it turns out that we can actually run PageRank on 200 machines with 1 trillion edges in less than 6 minutes in iteration. And we just presented these results last month at our Analytics at WebScale conference. OK. Yeah, a little self-congratulatory pat on the shoulder, right? So we actually have not focused on performance very much in this area, to be honest. We've mainly been focused on making sure that problems we want to solve can get solved at a reasonable time, and that actually, to be honest, for us, usability, as many of those speakers have mentioned, is the primary thing we want. So we've added all these features, master computation, composable computation, and sharded aggregators as a way to support lots of different applications. But just for fun, we had a couple interns this summer, and we have some free time, so we're like, let's just try to improve things a little bit in the next month. So we added some new improvements, and we were able to get this time down to 4 minutes. So for those of you who are doing the math, that means we're doing more than 4 billion edges per second on 200 machines. And I ran these last night. I'm sure they're right. Yeah. All right, so here's the roadmap. We just released a 1.0 community edition in just a couple months ago. We had a long break there where we weren't doing anything because this project was actually just started at Facebook in July of last year. So we've only been doing this for about a year. And we expect that in the fall we'll have another release which has some of these features we talked about. But everything actually is already available in trunk. We actually work off a trunk, so we feel it's pretty stable. And all our production code is running off a trunk. OK, so future work. Lots of future work to do. We want to look at alternative computing models. Lots of interesting things to see. GraphLab is interesting. Some partitioning things are interesting. Although, to be honest, Facebook friendship graph is actually not a power law graph. We published this actually in a conference, I think, in 2011, the anatomy of the Facebook graph. We limit the number of friendships at 5,000. And so you're not going to see a very nice distribution the way you'd see in some of the other pictures you've seen previously. And performance is something we continue to look at. To be honest, though, our customers are pretty happy with their performance. Most of the challenges we have now are actually getting more applications onto our system. We're looking at lowering the barrier to entry a little bit. So one thing we've recently added as support to Giraffe is Jython. So you can actually write some Jython code as a script and then run your Giraffe application without having to compile anything. But we're looking into other areas as well, such as maybe UI support and other things. And finally, applications. So one thing I want to stop and say here is that since December, so we started this project basically around last year, July. And by December, we already had a couple of applications running in production at Facebook. This last half, we spent basically getting more and more applications in production. We're powering different things in search, ads, feed, all kinds of areas in Facebook. And we're looking for basically broader use still. So that's our last area of future work. Thank you.